equilibrium is achieved, so there is a graph that we have to draw. So there was one graph between the speed versus time, and there was one graph with respect to the concentration versus time, right? So I had told you that when an equilibrium has to be achieved, right? So it is up to us that what kind of um, space or how much space we are providing to our reactants. Yeah. So if the space is more, so if the space is more, then what could have been the possibility? The third graph. So it was like CaCO3. If I heat it up, it gives me CaO and CO2. Yes or no? And let us suppose we had 100 molecules, and this time we had a bigger beaker. We had a bigger beaker. Let's suppose this one. So we had this beaker, Shruti, such a big beaker. And when we have such a beaker and the piston is here at the top, that means there's a lot of space. You understand? So when there's a lot of space, what would that mean? That means that, when it starts to break down 100 molecules, initially at T equals to 0, there was 0 CO and 0 CO2 molecules, yes or no? So if, let's suppose, at T equals to 0, 100 this and 0, 0, let us suppose at T equals to 5 seconds, I am left with just 20 molecules of this and 80 molecules of CaCO3 have converted into CaO and CO2. Why is that happening? Why is that happening? That is happening because CaCO3, when it breaks down, it gives me CaO and it gives me CO2 as well. But this CO2, Shruti, this CO2, this is getting a lot of space to move. So lots and lots of molecules of CO2 could be formed and they can acquire this much space. Are you understanding? So when lots and lots of molecules of CO2 are being formed, so I hope you're understanding that the speed, the forward reaction for a long time is going to be more because those molecules are obviously hitting the walls. Those molecules are obviously hitting the walls, but they're also, if they have to, hit back CaO, you understand? So there has to be large concentration of CO2 to do that. And this time we have provided a large volume. We have provided a large volume. Okay, which is why more and more CO2 could be accommodated. More CO2 could be accommodated. Are you understanding? And when more CO2 could be accommodated, Shruti, what would that mean? When more CO2 could be accommodated, that means there is this possibility that reactant, when it was decreasing, it has now decreased to such an extent that at t equals to 5 seconds, the amount of reactant left is way less than the amount of product formed. Can you see the molecules of CaO and CO2 are more? Do you understand? So there is also a graph that I can draw that at equilibrium what could happen. If this is my y-axis and if this is going to be my x-axis. So my x-axis represents what, Shruti? My x-axis represents time. Or I could say the progress of the reaction. Anything you can call it as. Right? And this is my y-axis, which represents the concentration. So I hope you're understanding that this point A represents what, Shruti? The point A represents the amount of concentration of reactants. It represents the concentration of reactants, isn't it? And the concentration of reactants here would be very high because it is at T equals to 0, we had this much amount of reactants. Yes or no? This much. But as the time passed, reactants were decreasing. And the reactants decrease how much? The reactants decrease from this value. So let's suppose this was 100, and this was 10, and this was 20, and this was 30 moles or 30 molecules, 40 molecules, 50 molecules, 60, 70, 80, 90, and 100. Are you understanding? So if it starts at 100 and it is now ending at, it is decreasing and decreasing and decreasing, and it becomes constant at 20. And then the products were 0, That was product, because at t equals to 0 there was no product, and it increased and it became constant after 8t. So this would be my line. So do you understand that why this line has become straight? That after equilibrium has achieved, that this beaker is no more able to handle more than 80 molecules of CO2. So the moment one extra CaO3 breaks, so you can imagine that it could become 19 CaCO3 molecules. And when it breaks, it is going to form 81 and 81, right, Shruti? And when it is going to form 81 and 81, the moment it happens, this A11 extra molecule, they will combine back again to form back 20. That means it cannot withstand a pressure of more than 80 molecules. So the moment the molecules of CaCO3 becomes 81, the reaction, the backward reaction is definitely going to take place at a faster speed and again create the product which is going to make it 2020. Yes or no? Okay, so that's the concept, Shruti. Secondly, so I hope you're understanding that there is no limit as to when for a particular reaction the equilibrium shall be established. It depends on different reaction, it depends upon different situations. Every reaction can be brought to completion. Do you understand? So if I even make the bigger beaker, there might be possibility that the products left would have been just 5, and the amount of the reactants left is just 5, and the products form are 95, 95. Are you understanding? So it's like equilibrium can be attained even at a later stage. So when I say that, so what do we understand? But once the equilibrium has attained, this value is not going to change no matter what you do. 95, 95, 5, everybody wants to stay at where they have reached. CaCO3 does not want to decrease below 5, and CaO and CO2 does not want to increase more than 95. Okay, so now when I see a particular reaction like that, so I hope you're understanding that when I say CaCO3 and it gives me, this is one reaction, right? CaO and CO2. So when I have CaCO3, it gives me CaO and CO2. And thereby, you understand, let us suppose, we had 100 molecules initially, and this was 0 and 0, right? At t equals to 0. So let us suppose at t equals to 5 seconds or whatever time, now the equilibrium has been attained at, let's suppose, CaCO3 has acquired only 20 molecules are left. This is left, okay? And 80 molecules and 80 molecules are formed. And we say that at this situation, equilibrium has been achieved. Equilibrium has been achieved, right? So if I take the ratio, if I take what? If I take the ratio of reactants over products, reactants over products. Why reactants over products, Shruti? Because they're not changing. So I can, I know the concentrations, I know the values. So can you understand that, the product that is CaO is my product, CO2 is my product, over the reactant is going to be my CaCO3. And these square brackets would represent the concentration, the molar concentration. Are you understanding? So I hope you're understanding, Shruti, that when I have CaO into CO2 over CaCO3, do you realize what is happening here? That this concentration, when it is not changing at equilibrium, yes or no? So if I put in the values, CaO I would put in 80 molecules per liter into CO2, I will again put it 80 molecules per liter or 80 moles per liter over 20 molecules are left. So now when I calculate 2 cancels 2 and it will be 2 times 4, so I will have this value as 320. Are you understanding? Okay, so this value, do you think that this value will remain constant for a long period of time? Definitely. Why do you think that this value will remain constant for a long period of time? Because we have calculated this ratio at equilibrium. And at what time? From 5 seconds and onwards, this ratio shall become 320 itself. It is not going to change beyond that. Right? So, can you imagine the situation in between? So, obviously, there would have been a situation. So, I am saying CaCO3 I'm saying CaCO3, it gives me CaO and CO2. So I am saying that, at T equals to 0, you said this is 100, this is 0, 0, ma'am. So don't you think that at T equals to 1 second, something might have happened that, in 5 seconds, let's suppose I say, 84 molecules are left, ma'am. So 16 molecules of this and 16 molecules of this are formed. So at this second, at T equals to 1 second, if I take the ratio of CaO, the products of the concentration of the reactant products over the concentration of the reactants. So this ratio would come out to be what, Shruti? 16 times 16 over 84. But I hope you're understanding that the moment it becomes T equals to 2 seconds. So again 16 molecules would be, decreasing. So when again 16 molecules decrease, what exactly happens, Shruti? Just tell me. So it would be 84 minus 16. So wouldn't that be 68 would be left and 16 more would be formed? Yes or no? 16 more would be formed. So now the Kc at T equals to 2 seconds would be what? Kc means the equilibrium constant would be what? 32 times 32. That is product over reactants, isn't it? So this value is continuously changing every second. Are you understanding? This ratio of product over reactant is not remaining constant. Are you understanding? And why is this so, Shruti? Why is this so? Why is this product not remaining constant? Because the reaction has not yet achieved equilibrium. It is about to achieve equilibrium at T equals to 5 seconds. At T equals to 5 seconds, this would remain 20. This would become 80, 80, and then beyond that, I cannot see a change. You understand? So this ratio, when we have achieved equilibrium, so this ratio of the product over reactant concentration, square brackets means concentration of products over concentrations of reactants. This ratio, I would be calling it as Kc, that means equilibrium constant. And other than that, I would call this ratio as Qc, that is called as a reaction quotient. Okay, this is called as a reaction quotient. So what do you understand from this? What do you understand from this? So we have the reaction quotient. It means that, other than any situation when we have not achieved equilibrium, this ratio of product over reactant shall be called as reaction quotient. And at equilibrium, this ratio would be called as the equilibrium constant. Do you understand? So that's the difference. Now understand one thing. So in any reaction, when I say N2, NH3 gives me, on breaking down, it gives me N2 plus H2 and I balance the equation. So I put 3 times H2 and I put 2 times NH3. So what shall be Kc, Shruti? In this, what is Kc? I am asking you to write down the equilibrium constant. And I am asking you to write down the equilibrium constants expression. First of all, you need to know the constants value you need to write down. So do you think that you would be writing it down as the concentration of the product of N2? Because N2 here is my product. H2 is also my product and ammonia is my reactant. R stands for reactant. P stands for product, right? So concentration of the N2 into concentration of H2 raised to a power equal to the stoichiometric coefficient. That shall be 3, Shruti, here. Over the concentration of ammonia raised to the power 2. That will be my equilibrium constant, Shruti. So what is the statement? It says the equilibrium constant. I'm not writing equilibrium constant because it's a long word again and again. So I'm writing Kc, but I hope you understand. Kc's equilibrium constant is defined as the ratio of the concentrations of product to the concentration of the reactants to the concentration of the reactants. CONC dot is concentration of reactants. With each concentration term, with each concentration term, CONC would not be meaning concentrated, it means concentration term raised to a power raised to a power equal to its stoichiometric coefficient. Okay? Equal to its stoichiometric coefficient in a balanced chemical equation. Right, Shruti? In a balanced chemical equation. Understood? That's the statement. So if I give you this particular equation, so if I give you 3 times A plus 2 times B, give me 5 times C plus 6 times D. So do you think that Kc shall be what, Shruti? C raised to the power 5 into D raised to the power 6 over A raised to the power 3, Shruti, into B raised to the power 2, isn't it? That shall be Kc. Okay? That shall be Kc. And thereby, so that's how you first need to know. And what is C and D? C and D, which is being formed at the time of equilibrium. And A and B, whatever, so the time when we have acquired equilibrium, whatever is left in the beaker for A and B, that concentrations we have to put in. So these are called as the equilibrium concentrations, not the initial concentrations. Because I hope you can see when we look at the concentrations, Shruti, they are not being the same. The initial concentration was 100 and 0, 0. And every second, the concentration of the reactants is changing. Yes or no? And the product is being formed. So at equilibrium, the values are different. Are you understanding? Right? So now, from the values of QC and KC, what do we analyze? So first of all, you have to learn one thing. You will be given a reaction and they will be giving you these kind of arrows here. These double-sided arrows would mean what, Shruti? These arrows, double-sided arrows. What do they mean? Tell me. These double, yeah, backward. Correct, correct. Okay. Also, you understand. So there is one more explanation to that, but the moment the question comes, I'll tell you that. But I hope you're understanding this much part. So every time you see a reaction, just simply write down this equilibrium constant expression. Okay. Now let's get back to the previous slide. Understand now. So do you understand that at every second I can calculate the ratio of product over reactant? Now you tell me, is the concentration of reactants, the reactants are increasing, isn't it? So at equilibrium, we have reached a stage for the reaction where the products are no longer getting produced, Shruti. So when the products are no longer getting produced, what would that mean, Shruti? That means this is the maximum extent up till when, in a given particular condition, the products could be formed. That you cannot create more than 80 molecules of CO2 because your beaker does not allow so. You understand? So that means what? That we have 80 molecules and 80 molecules. So do you think that at equilibrium, do you think the product would be maximum formed? Tell me. Because it is not, even if it tries to become more than 80, 81, 81, don't you think the reaction will move backward? So what I'm saying is that at equilibrium, do you realize that the amount of product that is being formed here, Shruti, this is my maximum product, isn't it? Because the reaction is not willing to proceed further than this. And the moment I provide it enough energy to within the same conditions, so do you think that it is going to become 81? Yes, momentarily it might become 81 and this might become 19, but the same moment it is going to return back also. Are you understanding? So I am saying within the particular conditions given, do you think that 80 molecules and 80 molecules that have been formed, this beyond this the reaction is not proceeding at all? So what does that mean, Shruti? Tell me. Tell me. So this value at Kc at equilibrium, do you think the product of the concentrations of the products would be maximum or not? Because at other positions, 32 times 32 would be less than 80 times 80, definitely. And the reactants at equilibrium would be as minimum as possible because it is not ready to decrease further. So, do you understand that, at all the times before the equilibrium has been achieved, you understand, at all the times the equilibrium has been achieved, the ratio QC, which is the reaction quotient, would be less than Kc, Shruti. Tell me. Because at when QC becomes equals to Kc and it is not changing further, we say we have achieved equilibrium. But when I say that there is also a situation that at all the times before Kc has reached, and when has Kc reached? When 80 CaO and CO2 is formed. So there might be a time where there might have been 70 CaO and CO2. But that time was less than 5 seconds, and that at that time the reaction was still, capable of producing more CO2 and it was not trying to go back because it could handle more CO2 in that situation. So I hope you're understanding that 32 times 32 over 68 would give me what, Shruti? This would give me reaction quotient, no doubt, but that reaction quotient value would be less than Kc. And what does it indicate? That the reaction is still trying to move forward? Yes or no? Because it is still lesser than Kc. It has not even achieved Kc. So the reaction can still move forward, and still there are situations where the values can increase, the ratio can increase to become equals to Kc, Shruti. Are you understanding? I hope you're understanding. That means to become equal to Kc, the value of Qc has to be increased. And how can you increase the value of Qc, Shruti? Qc is the ratio. Qc can be increased by increasing the numerator and decreasing the denominator because it's a fraction. Qc is a fraction. And a fraction can be increased by decreasing the denominator and increasing the numerator, Shruti. Do you understand my point? So if I have to increase the numerator, and in my numerator I have my products. And when I have my products, do you understand the products have to increase? And how do you think the products will increase, Shruti? When the reaction moves forward? Yes or no? When the CaCO3 breaks further to produce more CaO and CO2. Are you understanding what I'm saying? Sure? And now let us suppose I reach this situation where I forcibly, when I force the reaction to form 81 CaO1 CO2 and 19. So then if I calculate QC, because I know again I'm not at equilibrium. So then it would become CaO, the concentration of calcium oxide into the concentration of CO2 over the concentration of CaCO3, Shruti, isn't it? So that ratio would be what? 81 times 81 over 19. And this QC this time would become greater than KC. Are you understanding? Right? But we want to don't you think that the reaction wants to stay at just the equilibrium? Yes. So what did you understand from this? That the moment it becomes 81 and 81, it does not want to increase the concentration beyond 80 because of the given imposed conditions, the volume of the box and everything. So that condition does not allow the reaction to make more than 80 molecules. But if we force the reaction to produce more than 80, what would the reaction do? It would combine back, it would go back. Yes or no, Shruti? Which means what? That the moment QC becomes equals greater than KC, that means that's a forced reaction. The reaction is forced to produce as much even than its own capabilities. So the moment you remove the force factor, which could be extra heat, which could be anything which is extra being provided to the reaction or extra pressure, the reaction will move immediately backward. Why? Why is the reaction immediately moving backward? To restore equilibrium. To restore equilibrium. Are you understanding, Shruti? That's the concept. So if somebody asks you that, for a particular reaction, there is this QC and there is this KC, and they would ask you that, identify where is the reaction moving. What is the current situation of the reaction? Is it at equilibrium, or is it trying to move backward to restore equilibrium, or is it trying to move forward to restore equilibrium? Are you understanding? Okay, Shruti. So, like for example, if I give you this question, the question says, for a reaction, for a reaction, N2 plus 3H2 to form 2NH3. The Kc is 150 or 1500, and the concentrations of N2, H2, or let me say it is 1.5 into 10 raised to power 2 and NH3 are at T equals to 4 seconds is 0.1 molar, 0.7 molar, and 0.8 molar. Predict the direction of the reaction. Predict the direction of the reaction. That's how the question would be put up. So what would you do, Shruti? Tell me. So you will say, okay, Kc is given to me. So Kc is of no importance to me. Let me tell you. Why Kc is not important? The Kc is not important because it's 1.5 into 10 raised to the power minus 2, Shruti, here. 1.5 into 10 raised to the power minus 2 here. Okay? The Kc value. Why? Because it says it is asking me to predict the directions of the reaction. And it has given me the concentrations of N2, H2, and NH3, isn't it? So when you write down N2, when you write down H2, and when you write down NH3, you have everything with you. They have given you that at T equals to 4 seconds, how much and what is left, Shruti. So I would say the value of Kc shall be what? Ammonia. The product is ammonia. And the reactants are nitrogen and hydrogen. So ammonia over N2 raised to power 1 and hydrogen raised to power 3. And ammonia raised to power 2, Shruti, isn't it? So ammonia would be what, Shruti? Ammonia is respectively, it is 0.8 because I have written N2, H2, and ammonia. Ammonia would be 0.8 square. The concentrations raised to the power, the stoichiometric coefficient. What is the balanced stoichiometric coefficient? 2 over nitrogen would be what, Shruti? Nitrogen would be 0.1, and the balanced coefficient for nitrogen would be 1 here, isn't it? So I'm going to just put in 1 as a power. And for H2, I'm going to put in 0.7 raised to the power 3. Now, if I calculate this value, so I'm so sorry, I mistaken it. I should have written QC because I am not sure whether this value is at equilibrium or not. So it can be greater than Kc, it can be lesser than Kc, it could be anything, isn't it, Shruti? So if I say 0.8 square, so it would be 0.8 into 0.8. So that shall be 0.64 divided by 0.1 into 7 cube is 343. So it shall become 0.343. So if I even if I don't solve it, let me just see how much would that be, Shruti? It would be 64. If I remove all the decimals, it will be 64 over 1 into 343. And for 343, I'll put 1000 upper at the top. And for 0.1, I'll put a 10 at the top. And for 64, I'll put a 100 at the bottom to remove the decimals, isn't it? So these zeros gets cancelled, Shruti. These zeros gets cancelled, right? And thereby, I have 6400 over 343. What do you think you will have? You will have some value obviously greater than 1.5 into 10 raised to the power minus 2, Shruti, isn't it? Because it is 1.5 over 100. And 343 would be definitely greater than. You can divide it also. What is the value? Can you divide and tell me the answer? 18.65. See, such a big answer. So you said that, I have just calculated the ratio QC, which is 18.65, and this is greater than the KC. That means it is definitely a forced reaction. And now QC wants to decrease because everything wants to become equal to KC, right? Every reaction wants to reach its equilibrium. And the question has already told me the moment, the Kc value becomes this 1.5 into 10 raised to the minus 2, then definitely the equilibrium has been attained. But what are we doing in order to produce more and more amount of ammonia? We are forcing this reaction to sort of produce ammonia, and which is why a lot of ammonia than it could handle has been produced, which is what it shows that, the Kc, the reactant is so high and the product is way too less, which is why this value has been acquired. Yes or no? And thereby, this reaction, the QC would like to decrease. The QC doesn't want to remain QC, it wants to go to equilibrium. How would it go to equilibrium? The equilibrium value is 1.5. 1.5 over 100, which is a very, very small value, 0.015. And if that is a very small value, Shruti, it would mean what? Tell me. It would mean that 0.015 would be what? This wants to decrease. If it wants to decrease, it is going to go the backward direction. Okay? Because how would QC decrease? QC is product upon reactant. The ratio will decrease by reducing the products and increasing the reactants because it's a fraction. And how would the products will decrease? When ammonia will decrease, when it will decompose back to nitrogen and hydrogen, and the concentration of N2 and H2 would increase. I hope you're understanding the concept, Shruti. Okay? So these kind of questions you will be put up. Now understand also one thing. Can I rub it off? Can you understand this part? Taken the screenshot and written down? All right. So this is one question. So that will be put up. So now there is one concept here, Shruti. One major concept. So after this class, I primarily would be left with just the numerical part. Okay. So I would be done with the theory part of this chapter today. So now understand. So this is called as the Lee-Chatelier principle. The Lee-Chatelier principle. So I hope you understand the difference in the relation between the QC and the KC expressions, Shruti. Right? QC is at any time where the reaction is not at equilibrium, and Kc is the ratio of the product over reactant when, tell me, when when the reaction is at equilibrium. Exactly. Next we have is Lee-Chatelier principle, Shruti. Okay. Now this principle states that in an already established equilibrium, in an already established equilibrium, okay, if any changes, if any change is made with regards to, with respect to, or with regards to the concentrations of reactants or the concentration of product or pressure of the beaker, pressure inside the beaker, or the temperature or the volume, or we have added any inert gas, the equilibrium shall be destroyed, which is very much understood, Shruti. The equilibrium shall be destroyed. And it would try to again restore the equilibrium. And it would try to undo the effect of the change. It would try to undo the effect of the external change made. Of the external change made. Okay? That means it would try to restore equilibrium. It would try to restore the equilibrium. Now, when I say at equilibrium, we are there. That I hope you understand that the speed of the forward and the backward reactions have become equal. So equilibrium basically means this. That means the speed of the forward and the backward reactions are equal. Speed of forward reaction is equals to the speed of the backward reaction. Right, Shruti? That's what we mean at equilibrium. But when I say that the equilibrium is destroyed, what do I mean by this line? That the speeds have again become unequal and at least one reaction speed has increased. Either the forward has increased or the backward has increased. Right? So we have to tell that which direction speed has increased. So we say the reaction has moved forward. When I say the reaction has moved forward, it means that the speed of the forward reaction is increased and the speed of the backward reaction is decreased. So when I say we move the reaction moves forward, that would mean what? It would mean the forward reaction speed has increased. The reactions move forward, that means the forward becomes more than the backward. And if I say the reaction moves backward, that means the backward has increased and forward has decreased the speed wise. Because now the equilibrium has been destroyed. So obviously the backward and forward reaction speed would not be the same. Okay, so that's the concept. So when I'm talking about the Lechateliers principle, that's the basic meaning. Now understand this part. So for example, if I say this particular reaction, Shruti, if I say, there was A and A would give me B plus C. Let's suppose something like this. Okay. And I say that, at T equals to 0, we had 100 molecules and we had 0 B and 0 C. So at some time, after some time T, like say 10, 15 seconds, and I say, okay, we have attained equilibrium. And obviously, I cannot draw the single arrow. I have to make the double arrows forward and backward because equilibrium is achieved only in the reversible reactions. So when I say, okay, I am at, let's say, 60 molecules of A are left and 40 of this, sorry, and 80 of this and 40 of this is formed. Because according to my balanced equation, 1 mole of A gives me 2 moles of B and 1 mole of C again. Right, Shruti? So what would that mean? Tell me, what would that mean? It would mean, it would mean that, you know, now this is at equilibrium. We are at equilibrium with the reaction. That means it doesn't want to increase its speed much. It has attained equilibrium. Now let us suppose, what do I do, Shruti? I add, this was happening in a closed container, okay? And let's suppose I inject little bit more amount of C in the beaker. And when did I inject C? The moment it has attained equilibrium, I decide to destroy the equilibrium. I said, okay, you are running at equal speeds. I will add more C from in the beaker. I've added more amount of C. Let's suppose I've added 10 more molecules to C. Yes or no? So when I have added 10 more molecules of C, what would that mean? Tell me. No. So when A gives me 2 molecules of B and 1 molecule of C, and it is in equilibrium, and at T equals to 0, we had 100 molecules and it was 0, 0. And at T equals to some seconds, it becomes now 60 are left. And when one molecule of A breaks down, it gives me 2 molecules of B. So when I say that out of 100, 60 are left, that means 40 have been decomposed, 40 have converted into products. So when 40A has converted into products, it would form 80B and it would form 40C. And at this situation, we say that the equilibrium has been attained. Do you understand? Now, understand. When I say equilibrium has been attained, Shruti, it would mean that I am now in a situation that the reaction is just in a situation that, it would not proceed further. No more amount of B would be produced, no more amount of C would be produced. And now I decide to destroy the equilibrium. I know that they're in equilibrium. And I add or I inject in the beaker little bit more amount of C. Let's suppose 10 more molecules. Okay. Now it's like this kind of situation. Sometimes, the life is going fine and there's nothing, no, nothing is changing, everything's going smooth. And suddenly there is a change which you do not want, isn't it? So don't you think that you want to get back to the previous part? Okay, let's get back to the normal life again, isn't it? Right? So what do? We take certain steps that we do not want this change. Even if it is a good change, it takes time to adjust to a change. So same is the case with this particular reaction, Shruti. There's 40 molecules of C. When the reaction has attained equilibrium, every molecule, whether it was C, whether it was B, whether it was A, they were all in the smooth sailing. They were like, okay, now this is the life. No more changes after that. But now, similarly, at the same time, I added C. You understand? What would happen, Shruti? So now in the beaker, since 10 more extra C comes in, so we have in totality 50 C molecules momentarily. And for this moment, the moment we get 50 C, C will not like this change. C wants to get back to its previous equilibrium concentration, which would be 40. C says, I don't care about B and A. Don't change me. You understand? Don't change me. I want to remain at 40 because that's what I was that's where I was. And I have attained that equilibrium since within 10, like 10, 15 seconds. I don't want to change it. So what would C do? C will say to B that, I don't want to remain 50. Extra 10 C, I don't know where have they come from. I want to consume these. I want to reduce or get rid of these C. How can B help C, Shruti? It can say, okay, I'm ready to combine with you. Let's combine and form A so that you will become 40 again. Are you understanding? So the extra 10 that we have added from outside, the reaction will try to consume those extra 10 carbons today. Yes or no? You understand? So how would it consume? How would it consume? Those C, extra 10 Cs would be consumed with B. And you know that when one C combines with two Bs. So when I have to consume 10 C, don't you think I need 20 molecules of B from there? Tell me. So C would get back to 40 again, ideally, and that 10 molecules of C would require 20 molecules of B, Shruti. So 60 molecules of B would be left. Are you understanding? Right? Right? And then you know that one molecule of C would form one molecule of A. So do you think that 10 more molecules of A would be formed? So 60 were already there and 10 more came in. So now I would have 70 molecules of A, and now this would be my new equilibrium, Shruti. Okay, so in this new equilibrium, what has happened? You will say, ma'am, how have they attained back the previous situation? So not A, not B. They have not attained back because obviously they have also changed from the previous equilibrium to a new value. But C, it was C. We destroyed the equilibrium because of C. You understand? So whosoever creates a chaos, it's the responsibility of that person to bring things to normal, isn't it? So it's like C. C said, the entire equilibrium got destroyed because of me, because some of my molecules came inside the beaker somehow, I don't know how, but now they have destroyed my equilibrium. So I want to get back to the previous concentration. So C for itself creates a normal situation, that was the previous one, without caring about the other elements, and thereby we attain a new equilibrium Shruti. But do you understand that in order to attain that particular previous value of equilibrium for C, it has to move backward? Yes or no? Now you will understand the fact now. Now let us suppose I must have added. So I am not concerned with the values here, the 40 and 60. These were just to explain you. My concern here is that if I have these particular values, Shruti, if I have these particular values, just understand what would that mean, Shruti? It would mean it would mean that when I add C, extra C has to be consumed no matter how much. So then, with that C, do you think that in order to consume those extra Cs, the reaction will have to move backward because that's the only way it could consume itself? Tell me. If I add an extra C from outside, so to consume that extra C, do you understand that to consume that extra C, I have to move back? Are you understanding? Right? And when I'm talking about the 60 molecules of A, Shruti, what would that mean? 60 molecules of A, what would that mean? It would mean, it would mean that, when you add A from outside, let's suppose in the already established equilibrium, you are adding A from outside. What would that mean, Shruti? Tell me. What would that mean? It would mean that you will have to consume those extra A. Let's suppose you add extra A from outside, 10 extra A. So how would you? So now A was like, okay, I am at equilibrium for long and I don't want to change this concentration. It's like we have the value, okay, it doesn't want to change its condition. It's okay, smooth sailing. But suddenly when then these 10 extra A's come in, it wants to consume those extra 10 A's because otherwise then it becomes 70 and it changes its equilibrium value. It doesn't want that. So how would it consume those extra 10? By moving in which particular direction? Tell me. It will move forward in order to consume itself. Yes or no? And thereby, Shruti, thereby, can I conclude that if I add reactants in an already established equilibrium, so for some time, the forward reaction, speed of the forward reaction would increase. I would say the reaction moves forward. When I say reaction moves forward, what do I mean? That for that particular time, momentarily, the forward reaction's speed has increased. Yes or no? The forward reaction's speed has increased. Are you understanding? And for the products, Shruti, and for the products, what would happen? The reaction, if I add extra products from outside, so the reaction will, for that particular time period, will move backward in order to attain again an equilibrium. I would say the speed of the forward reaction has increased for some time. Speed of the backward reaction has increased for some time. And why so? In order to regain, in order to undo the situation. Undo means going back to the previous situation. So C is trying to undo the change that has been made in the concentration of C by moving backward. Understood. So if somebody, they would give you what? They would give you this kind of reaction. And they will give you the conditions. They will say that extra B has added. Identify where would the reaction or where would the equilibrium move. Where would the equilibrium move, Shruti? So what would that mean, Shruti? Tell me, where will the equilibrium move? So you will say what? You will say that when I've added B from outside, it will move backward because B in this example would be my reactant. Yes or no? Understood? Okay. Now let's take another example. Shruti, I'll be doing a little bit of longer class with you if that's okay, and no class for others today because I want to complete this topic and it's a long topic. It won't be completed even in the next class. So I would be doing it today, half of it, and then a little bit tomorrow. And tomorrow I'll be doing others class. Right? Okay. Now understand. So next is the effect of temperature, Shruti. Effect of temperature. Okay. Now, how do you analyze the effect of temperature? Understand. How do you analyze the effect of temperature? Just see. So when we have, CaO, let's suppose I take this reaction. CaO combines to form CaCO3. Okay. Now understand. Very, very important part that CaO for me is what, Shruti? It is going to be a combination reaction. I suppose you're understanding. Because CaO and CO2 both are combining to form one product. You understand? So when CaO is combining to form one product, I hope you're understanding that this is a combination reaction. Okay. So there could be a debate like, ma'am, it's a reversible reaction, so definitely it can be a decomposition reaction also. It would be, if you see from the product to the reactant side, it is a decomposition reaction. And if you see from the reactant to the product side, it is a combination reaction. So my point would be that this is my reactant. The left side would be my reactant, and this would be my product. And the name of the reaction depends upon how it is moving from left to right. That's the correct name of the reaction. Do you understand? And obviously, if it is reversible, definitely the backside would be decomposition. No doubt on that. But my point is that, if it is a combination reaction, always understand that during the two reactants combined, Shruti, heat is evolved. Heat is evolved. Are you understanding? So I am doing nothing. I'm just taking a beaker, closing them, and putting in some crystals of CaCO3, and closing the beaker, and putting in some amount of CO2. The green molecules here would represent CO2, let's suppose, and pushing down the piston. That's it. That's all I'm doing, isn't it? And just by pushing, what am I doing? I am forcing these molecules of CO2 to hit CaO molecules. Right? And when I'm forcing these green molecules to sort of, hit the blue molecules of CaO, I am increasing the rate of collision, Shruti, isn't it? Because I'm decreasing the volume. I'm bringing this piston down. So this was position 1 for the piston, and now it is at position 2. So these molecules, these green molecules will also have to be accommodated here in that less space, isn't it? So now there would be more collisions, isn't it? This is position 2. So if increasing collisions are there, I told you in the previous class that if the collisions are increasing, do you think that the product shall be formed, Shruti? More product shall be formed. Are you understanding? Okay, so increasing collision would mean more products would be formed. And we are, by bringing down the pressure, by increasing the pressure, by bringing down the piston, I am forcing the reaction to move at the forward speed, at the forward direction. So I hope you're understanding that, I could, without even heating, I can carry out a certain reaction. So you tell me now. So when this combination occurs, do you think that the beaker will have a certain temperature of itself? Yes. The beaker will have a certain temperature for itself. Why? Because then CaO and CO2 would be combining, and when a combination reaction takes place, Shruti, heat is evolved. Are you understanding? So the beaker will create a temperature for itself. The beaker will create a temperature for itself. Are you understanding? Understood. What does that mean, Shruti? What does that mean? It means it means that, every reaction creates for itself a certain temperature, and that temperature remains fixed for a long period of time. Are you understanding? That temperature remains fixed for a long period of time. Are you understanding? Okay. Now, let us suppose what I do. I take up this beaker and I put it in the refrigerator. Now, this is my refrigerator. Okay. So, I hope you can understand one point that the moment the reaction attains equilibrium, no more further combination is taking place. Are you understanding? The reaction has attained equilibrium, so no combination is taking place anymore. And understand one more thing. So, for example, if you want to break CaCO3, don't you think that you will have to give it heat? Because to carry out the decomposition, Shruti, you have to give it heat. Only then these crystals of CaCO3 will break down because they will have increased kinetic energy, then they will collide and they will break down, isn't it? So, CaCO3, when you heat it, so can I say the decomposition reaction? Because the backward reaction is a decomposition reaction. So decomposition reaction, Shruti, requires heat. Can I say decomposition reactions requires, I should say, or I should say absorbs heat? Yes or no? If it absorbs heat, Shruti, what would that mean? Tell me. If it absorbs heat, that means it is an endothermic reaction. So going forward, anytime if you see a decomposition reaction, just understand that this is an endothermic reaction, Shruti. Yes or no? And the combination reaction is what? The heat is evolved. That means it is an exothermic always. Yes or no? Tell me. Understood? So when I have the combination reactions and the endothermic and the exothermic part, the combinations are exothermic and endothermic is decomposition. So you tell me one thing. Like for example, if you're giving heat to something, okay, and the reactant immediately absorbs that heat. The reactant immediately absorbs that heat. So and it is doing something with that heat. It's like this. Understand the situation. It's like this, that this is some person. Okay, he's tired, and you give him some sort of bonvita, some energy. I don't know what drink do you have in UK, that is Horlicks or whatever, Protein X, I don't know. We have these in India. So you drink it and you get energy. So there are two ways to. So either this person A would do nothing, just drink bonvita, gain energy, and sit back. What is he doing? He is storing energy. Yes or no? But there could be other situation also that if he drinks bonvita, immediately he gets to work. What does he do? Whatever the gained energy he had, let's suppose he gained 100 joules of energy, he used that 100 joules of energy to work. So what did he store? 0 joules, isn't it? Because he's converting that totally into work. Yes or no, Shruti? So it is not storing. It is not storing. In the red portion that I'm writing here, the person in the situation B, for case 2, he is not storing energy. He is using energy. Are you understanding? He is using energy to do work. So entire energy that you've given to this person A has been used in the work. Are you understand? What my point here is that if I would have no increase in temperature for this person, okay? No increase in temperature for A. Now let us suppose I have, okay, this person. Now let us suppose you understand the same thing with this person also, with the reaction also. That in this particular reaction, if you're giving heat to CaCO3, what do you think CaCO3 is doing? Is it storing heat, Shruti? Or is it using heat? There's a difference. Is it storing heat or is it using heat? What do you think? Tell me. See, understand. If it is storing heat, it is doing nothing. Do you see that CaCO3 is doing nothing? I can see it is doing and breaking into Ca and CO2. That means it is using that heat. Are you understanding? So it's like if I give him heat. So let's suppose CaCO3 was at 10 degrees Celsius and I give it more heat from outside. So people think that, if you're giving heat from outside, the temperature should rise. So students argue with me that, ma'am, it is at 10 degree, you are giving heat from outside, it will become 15 degrees. But my point is that the temperature will increase only if it gains that heat and stores it with itself and do nothing with that heat. But what it is doing, it is gaining that heat and using that heat to do what? To break the forces of attraction between calcium and carbon and oxygen, isn't it? So the heat that I'm providing from outside is immediately, continuously being utilized to break the attractions between the calcium atom and the carbon atom and the oxygen atoms, and which is why CaCO3 is breaking down into Ca1, CO2. So no increase in temperature I can see, and it remains at 10 degrees Celsius only. Are you understanding, Shruti? Yes or no? And so I hope you're understanding the basic meaning that when heat is increased, it might not lead to the increase in temperature. Are you understanding? If I am giving you energy, it might not mean that you're getting fat. If you're eating food, that does not mean that you're getting fat. Why? Because we are doing work also. We are working out also. You understand? But if I keep eating all the day and I do not do any workout, then definitely there will be storage of fat. Then I will become fat. Do you understand? Now understand. So for example, I put this reaction in a refrigerator. And this refrigerator, the refrigerator is very cool inside. It's very cool. And this reaction beaker has created some temperature for itself. So you know that, normally also minimum refrigerators, we keep it at 1 degree, 2 degrees. So let's suppose refrigerator is 1 degree Celsius. And the reaction beaker for itself, let's suppose, has created, let's say, 30 degrees Celsius temperature. So who do you think is more at temperature? Obviously the reaction beaker. And for me, it is a hot reaction beaker. It's a heated reaction beaker. And this heated reaction beaker, Shruti, would do what? This heated reaction beaker, okay, will start losing energy to the outside surroundings because heat travels from high temperature to low temperature. Heat moves from high temperature to low temperature, isn't it? So heat would start moving outside. And when heat starts to move outside, do you think the temperature of this reaction beaker will start to fall? So let's suppose it becomes 28 degrees Celsius. Why? Because the heat has moved outside. And what is the job of the refrigerator? Job of the refrigerator would be to take that extra heat and throw it outside the refrigerator. Do you understand? So there is a fan running inside the refrigerators to throw that extra heat out. So the temperature outside the refrigerator, it would maintain at 1 degree because there's a fan running out. It would just simply throw all the extra heat outside through all the vents that we have in here with the beaker. Yes or no? So what is my point here? That now this reaction has created like this reaction, this particular reaction beaker, when it was at 30, it had created for itself an equilibrium situation. And in that equilibrium situation, it had maintained its temperature at 30 degrees C. And what have we done now? Tell me. We have kept this, we have kept this in the refrigerator. And we have reduced its equilibrium temperature from 30 to 28. Are you understanding? So do you think we have destroyed the equilibrium now? Isn't it? There was an equilibrium temperature that this reaction has created for itself. And what I've done, I have changed that temperature and I have kept it in the refrigerator. I have cooled down this beaker, and thereby the equilibrium temperature for this reaction that it had created, the heat that it had created for itself inside, we have done what? We have reduced, we have changed that temperature. So do you think we have destroyed the equilibrium? Yes. And when we have destroyed the equilibrium, Shruti, what would that mean? Tell me. It would mean that this reaction will try to somehow get back to the previous heat. You understand? This reaction will try to get back to the previous heat. It says I want to get back to 30 degrees Celsius. I will have to produce more heat because only then I can increase my temperature, Shruti. Are you understanding? Now, you tell me, where do you think the reaction will prefer to move where it can increase its temperature? What does the reaction need to do now? The reaction needs to produce more heat inside so that it can increase its temperature. Are you understanding? And how would it be able to increase its temperature, Shruti? By producing more heat. And how will it be able to produce more heat? In which reaction do you think heat is being produced? In the combination reaction or in the decomposition reaction, Shruti? In the combination. So where do you think in this particular equilibrium reaction the combination is taking place, either in the forward direction or in the backward direction? In the forward one. So I would initially, just the way I see the reaction, I will just clear it for myself. It would be exo and it would be endo. Do you understand? So I hope you're understanding that CaO would combine with CO2 to form CaCO3, and forward reaction helps the reaction to produce its own heat. Do you understand? So to get back again to 30 degree, it would move forward. So now can I conclude that if I decrease the temperature, Shruti, if I decrease the temperature, which temperature? If I decrease the temperature from the equilibrium temperature. So that, don't you think that the reaction would try to get back to the equilibrium temperature again? It would want to produce more heat then. And when it would want to produce more heat, it would mean that it had to move in the exo direction, whichever it would be. Sometimes, see, I could have written down this reaction like this also, isn't it? I could have written down this reaction as CaO plus CO2. Then you see the backward would become exo and the forward was becoming endo because forward was decomposition and exo was combination. Yes or no? Understood or not? Right, Shruti? Hmm? So now understand, if for example I heat it more, what do you think? If for example I heat it more, you know, rather than putting it in a refrigerator, I put this reaction on a flame and I heat it. And it was already established equilibrium. It had created its own equilibrium at that particular point. So it had its own temperature of 30 degrees. But I said, okay, I want to increase its temperature to, and I increase it, let's say, to 31. So what would the reaction do, Shruti? It says, I do not, you keep giving me heat. You keep giving me heat. I will not let that heat increase my temperature. Do you understand what does the reaction do? There is a possibility that you keep giving heat, but still the reaction is not increasing its heat. That is possible when that heat is immediately getting used up. Are you understanding? When do you think the temperature will not be increased? When that heat is immediately getting used up. Because the moment it doesn't do anything with that heat, it will start storing that heat. And when it stores the heat, then only the temperature increases. But the reaction does not wants to change its temperature. Are you understanding? It wants to remain at 30, which would have been its equilibrium temperature. Are you understanding? So what would it do? It would immediately start consuming that heat, Shruti. And where do you think, when it starts consuming that heat, do you think that heat is utilized always in chemistry to break the bonds? And the bonds will break, definitely it will go back to the endo side because that's when the heat is getting absorbed. Are you understanding? Right, Shruti. So can I say, if for an already, if I decrease the temperature, it wants to produce more heat. It wants to produce more heat. to get back to equilibrium. And when I increase the temperature, it would want to consume that heat to not increase the temperature and stay at equilibrium. So then it would be the endothermic side that the reaction chooses to move. So I'm not saying forward backward, because in every equilibrium reaction, Shruti, there would be both. There would be a combination. If forward, then the decomposition would be backward, and vice versa. It is your job to see which one would be my forward. If my forward is decomposition, then I call it as endothermic. And if my backward, and then obviously the backward would be combination, and combinations are exothermic. Do you understand my point? So this is the effect of temperature, Shruti. This is the effect of temperature. So for example, if I give you this particular part, if I say PCl5 breaks down to give me PCl3 plus Cl2. Do you understand what I mean by this process? PCl5 gives me PCl3 plus Cl2. Tell me, what do you think would you do? So forward according to you should be? Forward according to you should be, tell me? Endothermic? Because forward is becoming decomposition. And how do you think I can decompose a molecule when I break its force of attraction? How will I break its force of attraction, PCl5, if I give it heat inside? So I have to provide it heat. And thereby, the backward reaction in this example shall become exothermic, because I can see it is a combination. I can see that, PCl3 and Cl2 combine to become one. And that's the identification of a combination reaction. The reactants would be many, the product shall be one. So that would be my combination reaction. And now I say that, and now tell me, where would you think the reaction would move if I increase PCl3? If I increase the concentration of PCl3, if I decrease the temperature, Shruti? If I decrease the temperature, okay? If I increase the temperature in the already, and when am I making these changes? When the reaction is already at the equilibrium. Okay, so increase the temperature, decrease the temperature, PCl3 shall increase, and I have added PCl5. Why am I giving you? There are different ways of asking. The concept would remain same. And I'm saying that, I have removed some amount of chlorine, removed chlorine from the beaker. That's my question. So now you tell me, if I have increased PCl3, I have added PCl3 basically from outside. Would you think that PCl3 at equilibrium would like this change? Do you think it would like the increase? So if it is 10 at equilibrium, I have added 5 more, it becomes 15. It wants to get back to 10. It wants to consume those extra 5 molecules. Are you understanding, Shruti? So it would move backward, because PCl3 will consume itself by moving backward, isn't it? Then I'm saying I have increased the temperature. There might be some temperature for this beaker that it must have created for itself by moving and forward and backward, whichever way the heat is getting produced. So increase the temperature would sort of again destroy the equilibrium and will force the reaction to move in a certain direction. Where do you think the reaction would move, Shruti? In the endothermic direction. And in the endothermic example here is forward. So I would write down forward. That means for some time, momentarily, transiently, the speed of the forward reaction is increased way more than the backward reaction. Then it says added PCl5. Added PCl5. Yes, to the forward side. And removed chlorine from the beaker. Now, what have I done? At equilibrium, let's suppose chlorine must have been at 20, and PCl5 would also have been at 20, and let's suppose PCl5 left would have been 80, because initially I must have taken 100, isn't it? So my question is, I have removed chlorine. Let's suppose I've taken out 5 chlorines from the beaker. Taken out. So how many chlorines do you think I'm left with? Don't you think I'm left with 15 chlorines? And when I'm left with 15 chlorines, what would that mean, Shruti? Chlorine would not like this change either. It would say, I want to get back to 20 again. If I want to get back to 20, what would that mean, Shruti? Tell me. Exactly. To cover up, because then it would decompose. It will decompose PCl5 more. That okay, you cover up Cl2 because it has decreased somehow. So it will move forward. So that's how you have to think that, where would the reaction try to move to undo the change, to cover up that particular change, either the increase or the decrease. Understood the point? So we have considered the two factors up till now, that is the concentration, Shruti, and the temperature. So now all the questions regarding concentration and temperature you can answer. The third factor would be the pressure. Understand? Effect of pressure. Okay. Now the point is, in an already established equilibrium, when do you think the effect of pressure would actually matter? If at least one of the reactants or one of the products is gaseous. You understand? If at least one of the reactants or one of the products is gaseous. I hope you're understanding. Right, Shruti? Are you understanding? Because obviously you understand, you cannot compress a solid, you cannot compress uh, you cannot compress a liquid either. You can compress gases. So when I'm studying the effect of pressure, I hope you're understanding that effect of pressure would be considerably seen on a reaction beaker where there is an impact of where I can compress things because pressure likes to compress things. So effect of pressure first of all could be seen. Effect could be seen only. Effect could be seen only if there is at least one gaseous reactant or product. And I'm saying at least. It would be great if all of them would be reactants, if all the reactants and all the products would be gaseous. That is also possible. Okay. But at least if one gaseous reactant or product is there, then it is important to study the effect of pressure also. Okay. Now, there is one more term. So, along with pressure, I will cover up the volume part also. Along with pressure, I will cover the volume part also. What does it say, Shruti? It says that, the understand. If I say there's this beaker, right? And there is this piston. There is this beaker and there is this piston, Shruti, right? So, if I increase pressure onto it, what do I do? There is a certain piston right here. And I start keeping bricks over the piston. Where do you think the piston would move, Shruti? Tell- Right? Where do you think the piston would move, Shruti? Tell me. Where do you think the piston would move? No, I'm putting bricks. I'm putting bricks over the piston, and there is some gas obviously filled in inside. My point is, where do you think the piston would move? And there is this particular volume V1 available for the bricks. That was available when there was no brick. And now, when I've started to place these bricks onto each other, then how much volume do you think would be available for this particular gas? Would it be more than V1, or would it be equal to V1, or would it be less than V1, Shruti? Oh my God. You're pushing it downwards. The bricks have some weight. It is going to push it down. So the new position of the beaker would be here, Shruti. If it is at this height, if I'm suppose I'm making the same height, the piston would go down, isn't it? It's like a syringe. If you push it from backside, if you increase the pressure from the backside of the syringe, where do you think the piston of the syringe moves? It goes down. If you're increasing pressure from outside, the external pressure, the piston would move down, Shruti, isn't it? Right? So the volume would decrease. The volume would decrease, isn't it? So when is the volume decreasing? Tell me, when is the volume decreasing, Shruti? It is decreasing when you increase the pressure, the volume decreases, isn't it? And at 3 bricks, the piston stops right here. Why? Because obviously, when the gases are getting less space, when the gases are getting less space, Shruti, I hope you're understanding that it is hitting the walls even more now, because in the less space they have to move, so more number of collisions with regards to the wall, and when it hits the wall more, it creates a lot of pressure. So inside pressure is also increasing. Are you understanding, Shruti? Right, so that's my point. So I hope you're understanding. So here pressure inside was also less. Why pressure was less? Because there was more volume. Yes or no? So the molecules, because these molecules are moving, okay, but they are also colliding among themselves because they're hitting the walls after a long period of time. Because there's a lots of space. Here, what is the space? The space has reduced. So they would be hitting the walls more number of times now. Yes or no? Their frequency of hitting the wall would increase more. So now they would hit the wall more number of times. They would apply force more than the situation one. And when they would increase the force, Shruti, what would happen? Tell me. When it would increase the force, what would happen? The pressure inside would increase. I hope you're understanding what I'm saying. So there is a relationship between the pressure and the volume. That if you increase the pressure from outside, so the internal pressure definitely increases. And to cope up with that increase in pressure, the piston moves down, so the volume decreases. So I can say that when pressure increases, volume decreases. And vice versa. So pressure is inversely proportional to volume. So if you remove the bricks, if you start removing the bricks, Shruti, one brick you've removed, second brick you've removed, third, where do you think would happen? The gases will again push back the piston, and the piston will again come back to its own position. So now the gases will push back to acquire even more volume. Are you understanding my point? Understood or not, Shruti? So obviously I am lowering down the pressure from outside. I am reducing the pressure. I am reducing the pressure. Right or not? So what would that mean, Shruti? It would mean that pressure is inversely proportional to volume. So the moment I'm studying the effect of pressure, I am also studying the effect of volume. If I say that the pressure has increased for the reaction, where do you think the reaction would move? So I could also ask you that if I'm decreasing the volume, because that exactly means the pressure is being increased, where would the equilibrium shift? That's exactly the same thing, isn't it? And vice versa. I could ask you if pressure is decreasing, then where is the equilibrium moving? So if volume is and I could also ask if volume is increasing, where is the equilibrium moving? So now understand. So one thing is for sure is very clear that when we are moving, when we are talking about the uh, increase in pressure, the volume decreases. So I am very, very clear that there is a lot of increased collision. And when there is a collision, Shruti, in the very first class of this rate of reaction, we have learned that when collisions increase, the chances of the reactants combining to form products also increases, isn't it, Shruti? Are you understanding? So my point is just see. So if I take this particular beaker, Shruti, if I take a reaction, let's say N2 plus 3H2 is in equilibrium with 2NH3. Do you think that 2NH3 would be gaseous? Hydrogen would also be gaseous, and nitrogen would also be gaseous, Shruti, isn't it? And they're all, in a beaker. And we have space, this much space. Okay, so, okay, let me make this beaker a little bit more. Let me clear it off. So let's suppose this is my reaction. N2 plus 3H2 is in equilibrium with 2NH3. And we have this beaker, Shruti. And we have a lot of space for this reaction to occur. You understand? And this is the piston. So when there's a lot of space, you understand, here we have one and three molecules. So in all, in the reactant side, I have four gaseous molecules, Shruti. And in the reactant side, in the product side, I have two gaseous molecules. Are you understanding? What do you think is happening here? So when we have two molecules of ammonia and I have one molecule of nitrogen and three molecules of hydrogen, what do you think would happen, Shruti? There is a lot of space. So do you think one molecule, so let's suppose this red molecule is of ammonia and three molecules of hydrogen are there. So do you think that they would collide frequently with each other because there's a lot of space? They would collide so frequently. No, there's no chance because they might collide. I'm not denying the possibility of the collision, but there's a lot of space. See, understand, it's very simple. If there is a big room, if, exactly, if there's a big room and there are just four people, the chances that they will talk to each other is very, very, minimal chances because they would all be, in their own space because it's a big room. They would all be with their mobiles and stuff and they would not interact much. But if I close them in a lift, they are bound to interact. Something or the other, somebody or the other would speak up. You understand? So what am I doing? I'm saying that when there is a lot of space, the molecules have a lot of space. So four molecules would try to remain, you know, individuals. They would not try to hit each other, or they would hit very slowly, and the tendency for them to combine would reduce. Because it's a big space, more molecules can be easily accommodated. No need to talk, no need to combine, no need to collide. You understand? And if, for example, Shruti, if I reduce the volume, how do you think I should reduce the volume? Tell me. Tell me. Yeah, I can put in certain amount of bricks from outside and I can increase, I can push it down. When I'm pushing it down, I'm sort of applying pressure from outside. So I am increasing the pressure, thereby the volume shall decrease, Shruti. And now the same molecules, now if I bring the pressure, if I bring the piston right here, this is my new position. This is my new position. So now those one red molecule and this blue molecule of hydrogen, don't you think they would combine? They have more chances of colliding now. Tell me. And now if they have more chances of colliding, so they know that it is a less space. So it is very difficult for all of us to stay in this in this less space, because earlier the space was more. See, I'll tell you a better example. Understand? Like for example, if in your house you have 4 rooms and there are just 4 family members. Okay. So what would you do? Everybody would take up their individual rooms and everybody will have their individual beds and one bed for one person. So you are like sort of, expanding in all the rooms, exploring all the rooms. But let us suppose you are 4 people in a family and you have only 2 rooms. So, and 2 rooms definitely can accommodate only 2 beds. Then what would you do? Everybody would be like 2 people would be sharing one bedroom, one bed, isn't it? So, what does that mean? That when you have less space, you try to accommodate by squeezing down into that space. Yes or no? Now, let us suppose you have only one room. So there are chances that sometimes all the people are sleeping on the same bed because there's only one room but 4 members. So less space, but the members are the same. So don't you think that they would squeeze down to that particular space itself? Tell me. So that's the situation. So basically, these molecules of gases have no space to go. So they say that this is what we are supposed to live in, and this is a less space. So how do we? What do you think we should do to easily stay in that room? Don't you think they would combine? Because then they know if they combine, they will become 2 molecules, and then their life would be easy. They would get more space because two can then easily acquire. Two can still move faster and acquire, like, feel more spaces there. Are you understanding? Or you can also understand it this way, that small volume will accommodate less molecules easily. Okay, and large volume can easily accommodate large number of molecules, more molecules. Yes or no, Shruti? So if I'm reducing down the volume again and again, if I'm reducing down the volume, increasing the pressure, so I'm giving the molecules less amount of space now. Third time I would give them even less space. So do you think that they would move forward and reduce to 2 molecules by combining, because then they know that in the less space, less molecules can stay easily? Yes or no, Shruti? Are you sure you're understanding? Okay. So can I say the increase in pressure for a reaction will force the reaction to move in the direction to move from higher moles to lower moles, Shruti. To move from higher moles to lower moles of gases. You understand? And the vice versa. And the pressure, if you decrease, the volume shall increase. And more volume then will give them the liberty that, okay, you can acquire as much space as you want. So they would move from less moles of the reaction, less gaseous moles, to more gaseous moles. Yes or no? So now you tell me. So if I am giving you this particular reaction, did you take the screenshot? Is it, are you understanding? So for example, if I, for this reaction PCl5, which is gaseous, and I give this equation to you, it gives me PCl3, phosphorus trichloride, plus chlorine. And you understand that this must be taking place in some beaker. What do you think, Shruti? I am increasing the pressure. I am increasing the pressure. And these are all gaseous. So you understand on the product side, on this product side, PCl3 and Cl2 side, these are my products, right? PCl3 and Cl2. And PCl5 is my reactant. So on the product side, how many gaseous moles do you think I have? Write it down that. 1 mole of PCl3 and 1 mole of chlorine. So we have 2 moles. And on the reactant side, how many moles of the reactants do we have? Gaseous moles? 1 mole. And I am increasing the pressure, Shruti, isn't it? Yes or no? So when I increase the pressure, the volume of the beaker would decrease. And exactly. And when the volume is decreasing, the molecules will feel strained. They would not be able to, stay in that less space. So in order to get back the same relief, what would they do? Tell me. They would convert into a situation where less, even in the less volume, the reaction is stable. And in less volume, do you think only less molecules can stay? And how would the less molecules become? Then when the reaction, when the PCl3 and Cl2 combines from 2, they become 1. So they are moving from high moles to less moles. So in this case, the reaction would move backward because in the backward direction only, the reactants, the molecules could be decreased. Yes or no, Shruti? And if I would have said that, I have increased the volume, Shruti, increased the volume. So what would that mean in terms of pressure? I am basically decreasing the pressure. That means I'm removing the bricks out of the piston over the piston. And now if I'm increasing the volume, so more the space, more molecules can stay and freely. So it would move which direction? From less molecules to high molecules. Are you understanding? From less molecules to more number of molecules. And it would be from less to more, it would be forward. Yes or no? That's the concept, Shruti. That's the concept. So if anybody tells you pressure is increased, reaction is increased, you just have to count the gaseous moles. Like for example, if I say this, CaCO3, it is an equilibrium with CaO and CO2. Now in this example, only gas is CaO, CO2. CaO is solid and CaCO3 is also solid. Are you understanding? And now I say the pressure is increased, Shruti. So what do, you take the product side and you write down in the product side, there is only 1 mole of CO2. And in the reactant side, Shruti, there is 0 mole of CO2. There is 0 mole of any gas. You understand? There is 0 mole of any gas. And now I'm saying that pressure is increased, Shruti. When pressure is increased, what do you think would happen? The volume shall, the volume would decrease. That means the space in the beaker would, exactly. So in less space, would you think more amount of gas can stay or less amount of gas can stay? Less. So it would move from more moles of CO2 to less moles. It would move backward. Because then 1 mole of CO2 would also find it difficult to stay in that space. So it would say, okay, it's better to combine with CO and become solid and settle at the bottom of the beaker so that let the piston compress as much as it wants. I will simply settle down at the bottom of the beaker, becoming CaCO3, and it cannot compress CaCO3 as it is solid. Are you understanding the intentions? Right? So that's how you decide where the equilibrium would shift in order to attain a new equilibrium. And whosoever you are changing, that particular part, if you're changing temperature, if you're changing pressure, whosoever you're changing would try to acquire a certain amount of uh, what do you call, to acquire the reacquire the equilibrium. Understood, Shruti? Hmm? So this is my Lechateliers principle. The last concept is the addition of inert gas. The last concept is the change that we can make is the addition of inert gas, Shruti. The addition of inert gas. Okay. So addition of inert gas I can do at two different situations. I can do it at constant volume. I can add an inert gas to the solution at constant volume, and I can add an inert gas at constant pressure. Okay. At constant volume, if the question says that, we have added helium gas. What is an inert gas? It could be helium, neon, argon, krypton, xenon, and radon. So it would not say inert gas. It would say I have added neon in the beaker. So you understand neon is a noble gas. It is talking about this effect, this kind of change, addition of inert gas. And it says I have added neon at constant volume. Just simply say no change in the reaction. The reaction would neither increase the forward reaction speed nor it would increase the backward reaction speed. It would remain wherever it was. So no change in the reaction beaker at all. No change in equilibrium at all. Okay, no change in equilibrium at all, Shruti. And there is a reason also for that, but it is a pretty long explanation. So for now, just write it down. And it says that constant pressure, it says the result here would be similar to the increased volume. The result here would be similar to the increased volume. What do you think when the volume of a beaker or solution increases, Shruti? Where do you think the reaction beaker moves? Tell me. Where do you think the reaction beaker moves, Shruti? When there is more volume available to the reactants, it would move from less number of moles, less number of gaseous moles to high number of gaseous moles, isn't it? So the result would be something like this. Now, how it has happened, that we'll be doing it either tomorrow or after the vacations. Because I think we have guests over tomorrow. So there would be